So, hello everyone. I'm a machine learning engineer at DBI, and my talk will be to introduce real-time stream analytics, solution and scoring based upon Apache Flink and Cassandra and Druid. Basically, at DBI, we collect and process billions of events daily to track user engagement, habits, product and content performance, or any other interactions that may be of our interest. The goal is to provide customizable insights in real time based on custom metrics that are defined using self-created dimensions. The platform enables to perform various tasks from different domains, such as running AI-optimized marketing campaigns, adjusting the websites using real-time content performance analytics, fraud detection, anomaly detection, personalizing user experience using user profiling and AI scoring. So in terms of numbers, we do process around 100,000 events per second during peak hours. It's more than 10 terabytes of data daily. And we, in most cases, the data is available in less than 1 second from the ingestion to for querying. But it's not the scale of the data or its speed that is the most challenging for us. The more difficult part, at least in my opinion, is how to provide a customizable solution. And when we have, for every kind of data source, we have a different data structure. We ingest data in JSONs, which might be completely different. And also, the use cases may substantially differ. We need custom transformation, custom machine learning models, basically custom everything. So it's not about scalability of the data, but also scalability of operations and development. So to accomplish that, we built a solution that in general collects the data in the ingestion service. Then we put the data onto Kafka, and at the core of our platform, we use Apache Flink for event enrichment, AI model serving, custom transformations, alert engine, and so on. Then those process events are put back to Kafka and are used afterwards by different types of systems. First of all, we use Apache Druid for real-time analytics, which are available through an API or in a browser using our web panel. Also, we use Apache Cassandra to store the latest events, latest data for scoring, which is also available through an API. And we push everything to a data lake for data science purposes, basically model building, validation, testing, and the results are pushed back. The results, I mean, the serialized machine learning models are pushed back to Flink and are used for real-time enrichment. Okay, so in this talk, I will focus on Apache Flink, of course. To deliver our solution, we built a specific feature engineering framework that enabled us to provide reusable templates for data enrichment. Those features may be defined at runtime, may be changed. You may add them, modify, or delete those features using a control stream. And a specific type of feature is a machine learning model, which we also provide. Okay, so let's start with the first challenge that we started with, is how to provide a feature engineering framework like for almost anyone. Basically, it's not the developers or data engineers that create features. It's usually data scientists or data analysts that make up the requirements. And, well, in most cases, they don't know Flink, or it's good if they heard about Flink, but in general, they never built applications on top of Flink. This is like quite hard to learn. And even in most cases, then they don't code Java or in Scala, so like different words. So we created an abstraction layer for that. The general idea is quite simple. Basically, you have to define how to extract data that you need from a single event. Then you have to define how to reduce the information from the previous state and the current event. And finally, you have to define how to build, how the final feature should be built. This enables us to decouple business logic from operations, from the data pipeline. It simplifies unit testing of those features, really enables different teams in our company to contribute to feature engineering, like data scientists and data analysis. And what's also very important, it's much more harder to break anything. Basically, in the worst case, when you upgrade something, add new feature, the worst case is that the feature won't show up. Like, the pipeline will be working all the time, nothing happens. This is the simplest examples that you could define a feature in a code. So basically, it's the same as I said before. You have to define the name of the feature, of course, how to extract the data. This is a simple count example, so we count every feature, so we count every event, so we say that it's 1. To reduce the state and the current value, we sum just the values, and we return the state that was accumulated. Of course, this is a very simple example. You can do much more using that. We also enable to define dependencies between features. This is very powerful because it helps to reduce the state at least a few times in many cases. And also it enables us to define generic features that may be reused afterwards. So we don't have to re-implement it over and over again. Some of them are quite simple, like count or average, but some of them are more sophisticated, like approximate unique count or approximate top n frequent values on a specific dimension, for example. So we don't have to do it every time we define a new feature. And of course, coding in Scala or in Java is still quite difficult. That's why we tried to deliver something more. Basically, the question was how to enable to dynamically update our business logic at runtime without the need of redeploy. The answer is simple. It's even in the Apache Flink documentation. It's broadcasted state, and we use it, and it's very easy to implement. But the harder part is how should you define those features? When they should, in which part of the pipeline should they be computed? So basically, it's about serialization. We support few serialization formats for that. One of our first choices was portable format for analytics, because it enabled us out of the box to define simple business rules, or even more sophisticated ones, and even to serve machine learning models, out of the box. Also, as we have all the data in JSONs, we use JSON path to extract any information from a specific event. And some few more. One of examples, like we also can serve machine learning models here. Like we can freeze the TensorFlow graph and use it as a really simple transformation. Just add a new dimension to the JSON. Also, the one thing that you have to keep in mind is it's quite different when you have all business logic in coupled with your code. Here we have separate repositories for our Flink code base, Flink application code base, and separate repository for those features. So you have to think about how to provide, how to monitor the deployment, how to do the versioning. This also you have to think upfront, right? Here we have, I wanted to show you a simple example of how we can define those features. Those are definitions encoded in portable format for analytics. For us, the most useful case, most useful part of this specific format was that we don't have to invent our own language. We can reuse something that someone else did before, and it works well. Here we have the example of a simple comparison and some conditions on maps and so on. But it enables much more. There are like tens of functions that you may reuse, and even, as I said before, evaluate simple machine learning models. Not all of them, but the simplest one, yes. So, in terms of machine learning and serving machine learning models, the question is how to serve them like in the lowest latency as possible. If you want to use Flink, we have basically two options. We can embed the model into the pipeline, or we can use external model serving. Both of those approaches are valid. We tested both of them. The external model serving Flink has a very nice feature. It's called async function, and it works very well, and scale it's not that bad. And we also, of course, try to embed the models into the job. In general, we prefer the first approach, so model embedding into the pipeline. It's easier to maintain. Well, I would say like there are less moving parts. You have to, like, one part of the pipeline that you scale, you don't have to scale separately model serving and model usage, let's say. And the really cool part is that you may reuse the same pipeline that you've built before for model serving. So as I just copied the picture that I showed you before, you can reuse the pipeline the same way. You basically use the same transformation, preprocessing. The data is there when you serve the model, so there's no latency here. You can use the same tools for deployment. So we had a functionality of deploying features during runtime. We were able to use the same pipeline for machine learning models, so we just push them to Kafka, and they are instantly reloaded on Flink. It's easy to define A/B testing, versioning, and for analytics, for evaluation, we reuse the same products that we built. So we index the predictions on Druid for analysis, performance measuring. We can extract those predictions in real time using Cassandra, and so on. And of course, the data science team is able to evaluate on their own way using tools on Spark and so on. Okay, so there are two last slides, and that I wanted to mention. Two things that I wanted to mention is it's about evolution of jobs. Well, in case of stateless jobs, you just update the code and redeploy. If you don't touch the state, you just update the code and redeploy. The harder part is if you do something with state. It's sometimes maybe quite difficult. Some features need, like, for example, 90 days of data to produce valid results. Usually, we don't want to wait that long. So we do basically two things. One of them is, if it's really needed that we have to read historical data, we run two jobs. One is the current old job that is running on production, and it produces the output to the final topic. And in parallel, we may start the same job, but with newer version that is reading the same data, but from the beginning, and produces no output. And to switch them, we just have to disable the output for this one and enable the output for the other one. So basically, no downtime at all. It just switches. Also, there is a new feature in Flink 1.9. You can migrate the state yourself, but there are multiple talks about, so I will not go into details on this one. And of course, you can drop all the data from the data source and reprocess all the data again. This is usually not the case because it would take very long. Even it could be problematic to reload a single day. We have few situations when we had invalid data at the ingestion, and we had to reload some parts of the data. Again, if you don't have state, you have stateless transformation. You just reindex the data, preprocess, and push it to the final topic. But if you have a stateful operation, it's not only the raw data that you need, it's also the state. So to mitigate that, we periodically save point our jobs on a daily basis to be able to reprocess parts of the data again. And the last thing that you should take into account is monitoring and alerting. When you deploy the job on Flink, you basically lose control. It's working on its own. So every job that we deploy is we have monitoring tools. We use Prometheus and Grafana. And to be honest, it's not enough because usually no one looks at those dashboards. So alerting is the most important part for us. It's just we have to define specific alerts so that it comes to the right person and he knows what to do. So this is alerting is the most important. Failure recovery is just keep in mind it's not all about checkpointing. So that's not about temporary failure, but in some cases you have to reload the data and you need historical save points for that. And the last thing is you should also think about automating the pipeline deployment. It's totally fine if you have few jobs, but at some point you will have tens of them. So scripts for automated deployment, save pointing, and upgrading are really helpful for that. Okay, and thank you very much.
I wonder how you handle the data that's been produced onto the Kafka topic when you do failure recovery and replays and so on.
So it depends what case do you mean. In general, we retain the data on Kafka for 30 days by default. So if it's within those 30 days, we just if you know the offsets, we can start with a specific offset. If you don't know the offset, we can just read the whole topic again from a specific timestamp and using the old save point.
Yeah, but I mean the output data that's gone into Druid as well, maybe, and the output that's been produced. But so, do you ever have any deduplication problems of output where you're producing the same data over again?
No. In such a case, we just drop the data from Druid from those specific date. So it's pretty difficult because the minimum granularity that we have on Druid is we have to drop the whole day and reload the whole day. There's no possibility of reloading specific events or something like that.
No more questions? Then thank you, Michael.
Thank you.
Thank you all for coming. Thank you very much.